Shall we get started? So what was the last topic we were discussing? Sorry? We were doing some problems, right? Okay.
Yes, sir.
We'll do one thing. Let's move on to the next concept. Okay. So we discussed about electrostatic potential energy. So what was the formula for it? U is equal to minus K capital Q into Q naught divided by R, or I can write as Q1 Q2 divided by R, right? Then we calculated electrostatic force was KQ divided by R. Then we calculated the potential difference, which is VAB is equal to VA minus VB, right? These are all the facts we discussed yesterday, right? Now we'll go on to the next concept, that is electrostatic potential due to a dipole. So we'll see electrostatic potential due to a dipole. When I say dipole, again, what are the 2 points you are going to take into consideration? One is axial point, and the second is equatorial point. Okay. Listen. So first we will try to calculate at axial point. Okay. So if you take a system of positive and negative charge, let's say they are separated by distance 2a. Okay. And if I take a point P here, right? So if I say this is point A and this is point B, so all the distances are measured with respect to the center of the dipole. So from the center, let me say this point is at a distance R. Okay. Then how much is this distance going to be? R minus A.
R minus A.
Correct. And this distance is going to be R plus A. Right. So at point P, if I take it at point P, potential due to the charge at A is given by what? So what is the formula due to formula for potential? You have the formula in front of you. KQ by R. So K into Q divided by, what is the distance from A to point P?
R plus A.
So what will be the direction?
Along the
No, it is R plus A. Yeah. So what is the direction this? There is no direction at all. Because what is it? It's a scalar quantity. Okay. So don't make that mistake. There is no direction associated with it. So there is a potential due to the charge at point A. Similarly, the potential due to the charge at point B is how much?
KQ by R minus A.
Minus Q by R minus A. Yesterday I told you, for potential you need to take the sign of the charge into consideration, whereas for electric field you will not take. So the total potential at point A is equal to VA plus VB. So if I do VA plus VB, I write it as KQ into 1 divided by R plus A minus 1 divided by R minus A. So I got that minus because of minus q. Okay. So this will be equal to kq into r square minus a, sorry, r minus a minus r plus a divided by r square minus a square. Okay. So this is going to be equal to kq into r, and r will get cancelled. You will get minus 2a divided by r square minus a square. But what is the approximation we can do? R is very much greater than a, which implies r square minus a square is approximately r square. So when you do this, you get minus kq into 2a divided by r square. So this will be equal to minus k into, what is q into 2a? It is
Dipole
p.
moment.
Yes, it is p divided by r square. So this is the total potential at point P when the point P is taken on the right of negative charge. If at all you take the same point P on the left of positive charge, you will get plus kq by r square. So unlike electric field, what did I tell you in electric field? There was one important point if you make a note of it. You can revisit and tell me. So in the case of electric field along axial point, what is the important point I gave you as a conclusion? It always acts along the line in the direction of dipole moment. Whereas in this case, what will happen is it depends on which side you take point P. The answer came out to be negative here because the potential due to the negative charge is dominating. Why is it so? Because P is closer to the negative charge. So closer to the negative charge, more is the dominance. So that is why you got minus Kp by r square. You're able to understand? If you take on left of positive charge, what would have happened? It would have been plus Kp by r square. So there is not a standardized formula. Only the magnitude is standardized. But the minus or plus depends on which side you consider the point. Is that clear? Yes. Please make a note of it. You're able to see?
Is much smaller than where we was taking the A.
Where?
The numerator.
We will not take the total. It is A is very much smaller compared to A. It is a comparative degree. It is not absolute value. It's relatively low. So that is what a dipole moment. Dipole moment's definition is, what is it, guys? Magnitude of either of the charges into distance of separation between them. So Q multiplied by 2A is dipole moment. That is from the previous chapter. So I hope you're able to see and copy it, right? Said one chapter clearly. Other than the same thing, A is nothing but 2A is nothing but the distance between both the charges. A is half of the value. Right? Shall we move on to the next one? So it is the potential due to the charge A plus the potential due to charge B, because that is a total potential. It is not potential difference. Okay. Done. So we'll go on to the next concept. That is electrostatic potential due to a dipole at equatorial point. So second case, at equatorial point. Okay. So what is going to happen at equatorial point? If I take this as positive charge, negative charge, then if I take this as point P, right? So this distance will be, okay, the distance from the center to the point P is going to be R, and this distance is A, this distance is A. Then this is going to be root of R square plus A square. And how much is this distance going to be? It is the same root of
R square
R
plus E
square
square.
plus, yes, that's right. Now, if I take this as A and B, similarly at point P, right, the potential due to charge at A is how much? Potential due to the charge at A is how much? KQ divided by root of R square
R
plus
square
A.
plus E square.
What about VB?
Same, sir.
K
K
Oh,
minus
K
Q.
minus Q. Minus Q by R square plus.
That's right. So the total potential at point P will be VA plus VB. So what is VA plus VB here? It is going to be KQ divided by root of R square plus A square minus KQ divided by root of R square plus A square. The total value is going to be 0. So what is the meaning of it? You take any point on the equatorial axis, the electrostatic potential due to a dipole is 0. But is the electric field 0? What is the value? Check your notes. Okay.
The electric
AB.
field will be P by 4 pi epsilon naught R cube.
That's right. P divided by 4 pi epsilon naught R cube. Correct.
Minus P cap.
That's right. Okay. So I hope you're able to understand. You're adding it by a total. Total and sum. Yes. So total potential at point P. That's right. So when I say total potential at point P, it is going to be VA plus VP. Yeah. Okay. Done. The next point is how will you find the electrostatic potential due to the same system at any random point? Okay. At any point other than axis or equatorial. That is when it is making an not any point in the dipole, any point in the plane. So if this is positive and negative, if this is Q, this is also Q. Okay. So I'm taking a point P here where this distance is R1. Okay. If I take this point as O, this distance I'll take it as R, and this distance I will take it as R2.
R2.
Okay. So whenever you need to calculate the potential, right, or for that matter any value, then you need to ensure that your values are always in terms of dipole moment and the distance from the center. Okay. So what is the distance from the center? R. But you have two other values in this case. What are they? R1 and
R1
R2.
R2.
So R1 and R2, we need to start writing in terms of R and then substitute. Okay. But before that, let me start something like this. If I look at the basic definition, so VA is equal to how much? At point P, VA is equal to KQ by R1. VB is equal to or minus KQ divided by
minus Q by R2.
R2. So what is the total potential at point P? VA plus VB. I hope you're able to understand it is the total potential. So this is going to be KQ by R1 minus KQ divided by R2. Correct? So what will the value be? It is KQ into 1 divided by R1 minus 1 divided by R2. Right? But what are we going to do? We'll find 1 by R1 and 1 by R2 in terms of R itself. Okay. This is where little bit of mathematics is going to come into picture. Observe. So if I take this angle as theta, okay, then how much is this angle going to be?
180 minus theta.
Okay, I'm going with your textbook derivation. Now see, if I take the triangle POB, if I take the triangle POB, if I take this to be theta, this is A, correct? OB is A. What is OP? That is R. Then what is BP? That is correct. Okay. Okay. Now see, if I take a triangle, right? If I take a triangle, there are 3 sides and 3 angles associated with it, right? So the angle opposite to side A, the side opposite to angle A is called as small a. The side opposite to angle B is called as small b, and the side opposite to angle C is called as small c. Okay. You guys know what is sine rule? Yep. Sine A by A is equal to sine B by B is equal to sine C by C. Have you heard this? Right? Okay. In a way, like how sine rule is defined, there is something called as cosine rule also. This is very important. Listen, you need to know this to solve this. Okay. So cos A is equal to, what am I writing? Cos of A. See, generally, trigonometric functions are applicable only for, but here you don't have a right angle triangle. So cosine rule is applicable even for a scaling triangle. Okay, so cos A is going to be equal to, observe this, A is included by which 2 sides? B and C, right? So you write it as B square plus C square. Okay, subtract the square of the opposite side. What is it? A square. Is the numerator clear? I repeat it. Sum of the squares of the included sides. What is it? B square plus A square minus square of the opposite side, that is A square, and divide it with 2 times the included sides, that is B square. You have to understand. In a similar way, what is cos B? I want you guys to try it. What is cos B? C square plus A square 2AC. Okay, I'm not showing you the derivation or anything of this except it. Okay, you can prove it by dropping a perpendicular, take a right angle triangle and solve. You will get this, but that's not our headache. Our headache is only to take this and apply it in this scenario. Okay. Now I want you to use the same logic and tell me what is cos theta. Are you noting it down? Are you writing? You wrote the previous 2 derivations. You came late. Keep copying this. Okay, what is cos theta? A square plus R square minus R2 square divided by 2AR. Right. In your textbook, what they would have written is that 2AR cos theta would have been directly on the right hand side. Okay. So from this, what do I want? I want R2 square in terms of R. Right. So can I write R2 square is equal to, observe, A square plus R square minus 2AR cos theta. I skipped one step, right? So 2AR will go to the left hand side, it becomes 2AR cos theta. R square to the left, 2AR cos theta to the right. So when you do this, you will get this value, right? Now, I don't need R2 square directly. Rather, what do I need? I need 1 by R2. That's what the equation says. 1 by R2 is what is required. So to get that 1 by R2, first I will consider 1 by R2 square is equal to, okay, I'll take out, see, before that, sorry. R2 square is equal to, I'll take R square outside. Okay, when I take this R square outside, what will I get? A square by R square plus 1 minus 2A by R cos theta. Okay, so listen to this carefully. When R is very much greater than A, then A square by R square can be approximated to 0. Why? How I wrote this is very simple. See, R square minus A square, I approximated to R square, right? So if you are going to divide it with R square on both the sides, then you can approximate it to 0. That's what I did. Okay, are you able to understand what I did? So divide it with R square. So 1 minus A square divided by R square is approximately 1. So this 1 and 1 will get cancelled. A square by R square is approximated to 0. That is a mathematical operation. So what can I do in this equation? In the equation which I have on the, in this equation, what can I do? A square by R square, I can approximate it to 0. Accepted. Right. Then what is that I'm left out with? Always remember, when the values are very much greater, right, you should always ignore the squares. You should not ignore the exact ratios. A by R is not a small value. A square by R square is a small value. So R2 square will be equal to R square into 1 minus 2A divided by R cos theta. Right. Is it clear? Right. But as I told you, we need 1 by R2, 1 by R2. So 1 by R2 square, I can write it as 1 by R square into, observe the way I'm writing, 1 minus 2A by R cos theta to the power of minus 1. Is it the reciprocal? It's not the inverse. It is reciprocal. Right. So I will take 1 by R2. 1 by R2 will be equal to 1 by R into 1 minus 2A by R into cos theta to the power of minus half. Minus 1. Okay. So I just want to repeat certain things. One mathematical operation that we applied here is, see, I'll tell you, with this step, that is with equation number 1, physics part is over. You're all taking the help only from mathematical operations. Okay, in those mathematical operations, the first rule that I used is cos rule or cosine. Okay, more specifically, it is called as cosine rule. And after the cosine rule, I applied the approximation A square by R square is 0 and A by R is not ignored. Right. Then I wrote R2 square as 1 by R2 square. But on the right hand side, one of the parameters, I didn't write it as 1 by something. Rather, I wrote it as reciprocal of it. What is it? 1 minus 2A by R cos theta to the power of minus 1. Then what did we do? We took square root on both the sides. When you took square root on both the sides, you get this value. Now, the last mathematical operation that we're going to apply here is, if you have 1 plus x the whole power n, then this is approximated to 1 plus nx if the value of x is very much less than 1. Try to understand this. If the value of x is very much less than 1, then 1 plus nx is approximated to, 1 plus x the whole power n is approximated to 1 plus nx. This is a part of your binomial theorem. Okay. Here, what is happening is, observe, what is the range of cos theta? Minus 1 to 1. So it is a fractional value. And I told you in the beginning that R is very much greater than A. Then what can you say about A by R? When R is very much greater than A, then if I divide with R on both the sides, A by R is very much less than 1. So this value is a number which is very, very, very small. What do I mean by very much less than 1 is, it's a very, very small value. That is the meaning of it. Okay. Can I apply this theorem here? Because it is of what format? 1 minus a number which is very small raised to the power of some n. Here n need not be an integer, it can be a rational number also. So if I have to apply this rule here, then how should I write this step as? 1 by R2 is equal to 1 by R into 1 minus is already there. Here you have minus half. So what will happen? 1 plus half into 2a by R cos theta. Did you get that? Understood how I got that half? Half is the power that has come. So 2 and 2 will get cancelled. Then 1 by R2 will be equal to 1 by R into 1 plus a cos theta divided by R. Let this be equation number 2. Okay. So I suggest everybody to copy this first. And while you're copying, if there is any doubt, ask. See, this is how they have done in your textbook. So I have to explain it, right? So write it down. Tell me. If I zoom in, it will go out of box. So there's the screen size. Maybe I can keep it like this. So from where are you supposed to copy? From here. Is everyone supposed to copy from there only? Yeah, please write it. The other 2 points were axial and equal. We have not yet completed. 1 by R2 will be equal to 1 by R into 1 plus a cos theta by R. Scroll down.
So the same rule is also applicable for right hand.
But right angle triangle by default cost is applicable. Want to scroll down? This one?
Sir,
Yeah, tell me.
can you explain this part again? Cos A is equal to B square plus C square minus A square.
Yeah, see, this is A. I'm using red marker. You're able to see?
Yes, sir.
So this is A, no. If you're writing cos of a particular angle from the triangle, then see what are the two sides that is holding this angle. They are B and C, correct?
Yes, sir.
So it is the square of the sum of the squares of those two sides. That is B square plus C square. And you should subtract the square of the opposite side, that is A square. And divide the whole expression with 2 by default, multiply it with the sides which are including it.
Okay, sir.
Got
And if
it?
it was sin A, what should we have done?
Sin A, you don't worry about it. Sine rule is completely different. Here we are applying only cosine.
Okay, sir.
It's time specific only to this derivation. Right? So copy it faster.
So you are saying that voice is greater than E. Why are you not knowing that 2K by R?
2A by R is very much less than 1. A fractional value very much less than 1 can't be ignored. But the square of it can be ignored. See, 10 power minus 3, you cannot ignore. You put in the, but if you square it, what is going to happen? Means you are pushing the decimal values to 3 more points. It becomes even more small value, which is approximated to 0. If you ask me, is it exactly 0? No. It is approximated to 0. That's why I always put that symbol, the approximation. Okay. So write it down. So I hope everybody drew the diagram, right? You've drawn it. Now see. So is there anyone who's copying? Yeah. Which step? You're done. Okay. In a similar way, if I take the other triangle, what is the other triangle that you have? P. This is PAO. This is going to be 180 minus theta. This is R. And how much is this value? R1. Correct? Now, if you use the same logic, tell me what is cos of 180 minus theta that you're going to get here. So this is A square plus R square minus R1 square to AR. But cos of 180 minus theta is minus cos theta. Second quadrant, right? So it is going to be minus cos theta is equal to A square plus R square minus R square R1 square divided by 2AR. Now what I'm going to do is, I'm not going to write the whole step again. I will say, similarly, you will write these two steps, and from here you can directly write 1 by R1 is equal to 1 by R into 1 minus A cos theta by R. Why did I write 1 minus? Because if you see the previous steps, on the left hand side it was cos theta, right hand side it was similar expression. Right? When it was plus cos theta, what did 1 by R to give you? It gave you 1 plus A cos theta by R. In a similar way, if you start with minus cos theta, what is it going to give you? 1 minus A cos theta by R. You can call it like mathematical induction also. It's not the exact thing, but just the logic. See, here you started with cos theta. No? A square plus R square minus R2 square by 2AR. A square plus R square minus R1 square by 2AR. Right hand side is similar. But what is the left hand side on both the sides? In both the cases. There it is cos theta. Here it is minus cos theta. So when you started with cos theta, what did you get? You got a plus. When you start with minus cos theta, you will get a minus. Okay. If you want, you can solve and see, you will still get it. That is up to you. Okay. Now, what is the potential at point P? It is VA plus VB. Then how much is it going to be? KQ, if I take it out, what is the first equation? 1 by R1 minus 1 by R2. No, 1 by R1 is 1 by R into 1 minus A cos theta by R minus, what is 1 by R2? 1 by R into 1 plus A cos theta by R. So what will get cancelled? So I can take out R from both the sides, KQ divided by R into, I'll just write an extra step. See, 1 minus A cos theta by R minus 1 minus A cos theta by R. 1 and 1 are gone. Then what is that you're left out with? Minus 2 times KQ into A, or I'll write it as KQ into 2A. 2A into cos theta divided by, you have an R here and an R here. It is going to be R square. Right? So, Q into 2A, what is it? So, minus KP cos theta divided by R square is what is the value for this particular step. Okay, for this particular scenario. Now, listen, even before you copy it, okay. In the first case, at axial point, okay. So, I started with something like this. A, B. If at all I take the point P here, then what is the angle made by R with the axis? So what is the angle made? It is 0. So in this case, can I say theta is equal to 0 degrees? If I take theta is equal to 0 and substitute it here, I'll get minus Kp divided by R square. Is that not what you got in the first derivation? Right? Now see. In a similar way, if I take the same axial point, if I take the point P on the left hand side, then what is the value of theta? Theta will be 180 degrees, because this is what is theta. Theta will be 180. If I substitute 180, Kp into cos of 180 degrees, sorry, minus Kp into cos of 180 degree divided by r square. What is the answer? Plus Kp divided by r square. I told you, when you take it on the left of positive charge, you will get positive value, right? In a similar way, second case, equatorial. So what about equatorial point? Theta is equal to 90. So minus Kp into cos 90 divided by r square. Answer is, that's what you got with respect to equatorial. So there is like a general equation. Are you able to understand? So that's what we try to derive. So till where did you guys copy? Is this fine? Okay, copy it. Make it fast.
Sir, 1 minute, can you scroll up?
Scroll down, upper or down?
This is fine, sir. Thank you, sir.
Yeah. Shall we proceed to the next one? So this one. The next topic we are supposed to see is called as equipotential surface. Okay, so write down the heading as equipotential surfaces. Okay, so you try to break the word into two parts. Equi is equal. Potential is obviously potential. So you talk about a surface, right? If you have a particular surface which has the same potential at every point or zero potential difference. Listen to the statement carefully. What did I say? If you take a surface, see, for example, if I take this phone, if you take the surface and you take any point on the surface, and if every point is having the same potential or the potential difference between any 2 points is zero, then you call that particular surface as an equipotential surface. Okay, so if you see, so write that down. An equipotential surface is a surface with constant value of potential at all points on the surface. So it is there. See, first line is a surface with a constant value of potential at all points on the surface. Okay. So So an equipotential surface is a surface with constant value of potential at all points on the surface. Now see, we are supposed to draw the equipotential surfaces for different kinds of charge distribution. So remember in the previous chapter, we had something called as electric field lines for different kinds of charge distribution. What were the different charges we saw? Isolated positive charge, isolated negative charge, system of like charges and system of unlike charges, right? In a similar way, if you take a point charge here, if you take an isolated point charge, that can be a positive charge or a negative charge. Unlike electric field, since here you don't have any directions associated with it, the equipotential surface will take the same shape. Okay, so what shape is it going to take? Is a question. We're able to see what shape does it take? It's not circle, it's a sphere, because it is going to be three-dimensional. So if you take a point charge, right? So what is the definition telling us? From that point charge, so with respect to that charge, you need to draw a shape. And that shape should be in such a way that if you take any point on that shape, it should have same potential, right? So if I take a point P here, which is at a distance R, if I take another point P here, which is at a distance R, if I take another point P here, which is at a distance R, in a two-dimensional plane, it forms a circle. In a three-dimensional space, it forms a sphere. That is the meaning of it. So how to draw this? There is the way we draw, right? The next question is, how are we going to draw the field lines? For the same charge, if I ask you to draw the field lines, how will you draw them? The field lines are radially outward, right? Whereas had it been a negative charge, they would have been radially inward. Okay, so there are two important things that we are going to cover from here. Though the topic is equipotential surface, for a point charge, we understood how we are supposed to draw the equipotential surface. I hope that is clear, right? Now, with respect to the same point charge, if you draw electric field lines, you are able to understand that they are radially outward. So if I have to measure the angle made by the electric field lines with respect to the equipotential surface, what will it be? It is 90 degrees. Why? Because at that point, where is the angle measured? Angle is generally measured between two lines. Whenever you want to measure an angle, you need two lines. So electric field line in this case is definitely a line. Whereas you have an equipotential surface. What was my question? What is the angle made by the electric field line with respect to the equipotential surface, which is curved? Does it make sense? You need to draw a tangent. That is what we meant. So at the point where it is cutting the equipotential surface, draw a tangent and you measure the angle between the tangent and the electric field line. That is going to be the angle between electric field line and whom? Equipotential surface. One important point to be noted here is there are two ways to draw. One is if it is this kind of a simple system, then you can draw based on the concept of distances. That is what I did. I took all the distances. I understood it's a circle, right? Whereas when the system is complicated, it is difficult for us to draw. But there is one more fact that is helping us. What is it? Electric field line is always perpendicular to the equipotential surface at every point. This is a very, very important point to be noted. What am I trying to say? Electric field is always perpendicular to whom? To the equipotential surface at every point. Please make a note of it. Electric field lines are all, yeah, I repeat it, listen. Electric field lines are always perpendicular to the equipotential surface at every point. How is it? Because whenever you draw radial, right? So you know the fact that with respect to a circle, you draw anything perpendicular to that circle, you will always pass through the center. So with respect to the equipotential surface, where is the center? Recollect the concept from your 10th standard math. So with respect to the circle, the center is at the point where the charge itself is placed. So electric field lines are coming out from there. They are coming from the same point, right? So they are radially outward, means they are perpendicular to the surface at every point. That is the meaning. Okay. So see, what I am trying to say is at this point, if you draw a tangent, can you Can you confidently say that there is going to be 90 degrees? Because this line, the electric field is passing through the center. Okay. Only the perpendicular is drawn to the tangents will pass through the center. Right. Next. If
Sir,
tangent, electric field itself has a direction here. Tangent will give you the direction of electric field on an electric field line, not on equipotential surface. Which one? Over there it is a. No, it is not similar. It is not similar because you're trying to draw different kind of surfaces. Maybe once this is over, right? You're only only one concept by now. So you need to see for other systems of charges, then you decide. Okay. Yeah, somebody online they were calling me. What is it?
yes, sir. So here we are clearly considering only positive charge. So it's not that
No,
for negative charge. So
No, it is applicable for negative also. For whether you talk about positive charge or negative charge, equipotential surface is still a set of concentric spheres, but the direction of electric field will be different. So I'm drawing it here. You're able to see.
yes, sir.
Yes. So this is only you're able to observe the difference between this diagram and this one.
Yes, sir.
Yes. Okay. Now the next question is: if you have a charge which is placed at infinity. Right, when the charge is placed at infinity, then how are the set of electric field lines going to be? They'll be parallel to each other, or I can say you have a system of you have a system which is generating uniform electric field. So can you give me an example where uniform electric field is generated? You talk about a plane sheet, right? So when you talk about plane sheet, what is the value of electric field produced by it? Sigma by 2 epsilon naught, right? It is independent of R, correct? So if you have this kind of an electric field line system, right, then how is the equipotential surface for this going to look like? I just now told you equipotential surface is always perpendicular to electric field line. So what are you supposed to do? If you draw a set of plane sheets perpendicular to the electric field lines, then they will be the set of equipotential surfaces for a uniform electric field. So that is the heading. Equipotential surface for uniform electric field. If somebody asks you, what will you say? It is a set of parallel plane sheets. Okay, I hope you are not confused. This plane sheet is not the source of charge. This plane sheet is the equipotential surface. So yeah. Similarly, if you have a dipole, so if you have what you have a dipole, then for the dipole, then the equipotential surface is going to look something like this. They will not touch each other. Okay, they will not cross each other at all. Similarly, if you try to draw the equipotential surface for a system of positive charges or system of negative charges, that is system of like charges, then this is how the equipotential surface are going to be. Okay. Now you can ask me, how is this happening? Because if you talk about a dipole, then this is how the electric field lines are going to be. You have to understand, this is how the electric field lines are going to be. Then, based on these electric field lines, you draw tangents perpendicular to the electric field lines. So if you draw the tangents perpendicular to the electric field lines at every point, and you join all those points, then the shape you are going to get is what is the equipotential surface. Here we are doing a reverse analysis. See, because I'm using the word tangent, there might be a slight confusion existing. Listen to this very carefully. When you have electric field lines itself, in the sense you have an electric field line like this, if you draw a tangent to the electric field line itself, okay, if you draw a tangent to the electric field line itself, what does it tell you? It gives you the direction of electric field. Whereas if you draw a line perpendicular to the electric field line, what will it give you? It will give you a point on the equipotential surface. So like this, if you have different sets of lines, you draw tangent at every point, whichever point The perpendicular is cutting. You need to join all those points to draw that equipotential surface. It's like a construction method. Right. So are you able to understand? So this is how the equipotential surfaces are drawn. So these two things you can look at your textbook and draw it later. But is the concept clear? Right. Now, there is one type of question that they can ask you is, if at all there is an equipotential surface, okay, you have an equipotential surface due to whatever charge, due to whether you have an isolated charge, uniform electric field, dipole, light charges, anything, you have an equipotential surface and you have a test charge Q naught, which is moved along the equipotential surface from one point A to another point B. Okay. Now they'll ask you the question, what is the work done? Answer is 0. Why? Because, yes, we know this formula, right? Work done is equal to Q into potential difference. See, W is equal to QE down. Instead of V, I'm writing it as VAB, potential difference between point A and B. So Q naught is not a, Q naught has magnitude. But what about the potential difference between any two points on equipotential surface? It is 0. That's what the definition says. So answer is 0. So what is the important conclusion you can draw from here? If you try to move any charge along the equipotential surface, the work that you're trying to do is 0. There's an often asked 1 mark question. So keeping the marks aside, you need to know this concept to solve certain problems. This might be a hidden data also, right? But you need to know this concept. Am I clear? Please make a note of it. So what did I tell you? Any charge moved along equipotential surface, then the work done is 0. So write down the reason below. W is equal to Q into VA minus VT or VAB, and VAB is 0. Any charge moved along any, so if you move any charge along equipotential surface, work done is 0. Sharia? Work done is 0. And this is the reason. Okay. Next. So having this point in mind, we will try to find the relation between electric field and potential. So we try to find the relation between electric field and potential. Okay. See, suppose, look at this diagram. Okay. There's a very, very important relation. Please observe this. To apply it at many places. Okay. So let's say there are two equipotential surfaces. What are they? You have set of two equipotential surfaces. The meaning of it is, you have these spheres, right? I told you that these are concentric spheres, right? So when you see it from the side, how is it appearing? Like when you observe it in your paper, how is it appearing to us? You feel like it is a circle. Whereas when you see the same thing from the top, when your eye is here, you will be able to see it like a sheet of this form. Right? Suppose there is a source here. It need not be a point. So I'm just saying there is a source. For that source, let's say this is the first equipotential surface, and slightly above that, at a distance of delta L, we are considering an other equipotential surface whose potential is, I will take it as V minus delta. Why did I take it as V minus delta? I'm not going with the textbook. So there's only change I want you to make if you have your textbook. And see, this is the source. From the source, you're able to understand which one is at bottom and which one is at top. The diagram is clear, right? So the first one that I have marked is at the bottom. So let's say every point on that particular equipotential surface has a value V. Okay. At a distance delta L above that. How much? At a distance delta L above that, I'm considering a parallel equipotential sheet. I'm taking a small portion of it. Then I'm saying every point on that equipotential surface has a value of V minus delta V. Why did I put that minus? distance. It is at a greater distance. As the distance is increasing, the impact decreases. That is the reason I wrote V minus delta V. They wrote it as V plus delta V. That change alone, you can make it. Okay. This is delta L. I hope it is clear till this point. Now let's say I have a test charge Q0. What do I have? Potential will decrease. That's what distance increases, impact decreases. Sorry, distance increases, impact will decrease. That's what I meant. That is why I wrote V minus delta V. Okay, there is a test charge Q0 which is moved from one equipotential surface to another in the direction perpendicular to it. Sorry, what did I say? Q0 is moved from one equipotential surface to another, the parallel one, the second one, in which direction? Perpendicular to it, means along this line. To put it in simple terms, it is moved in the direction of electric field. Think about it. Perpendicular to the surface is parallel to electric field. Does that make sense? Think about it again. I'll give you time to process. Perpendicular to the equipotential surface is parallel to the electric field. Does that make sense? Yes, because what did we say? Electric field is always perpendicular to the equipotential surface, and you are moving it along the electric field itself. Now the question is, what is the force experienced by this discharge due to the electric field of source charge? Can I say force is equal to charge multiplied with E? F is equal to QE. So Q0 is the charge and E is the electric field due to the source charge. So Q0 into E. Accepted? Now, what is the work done by electric field? Work done by electric field is equal to Q into E into delta L. Why? F is cos theta. F is cos theta. And theta is how much? 0. Because you are moving it along the force. So force and displacement are in same direction. So cos 0. So can I call this as equation number 1? So what did I do? I borrowed the concept of work done from mechanics. That is why I wrote Fs cos theta. Now the same work done, I'm going to borrow it from the concept of electrostatics. So according to electrostatics, what is work done? Work done is equal to the charge that you're trying to move multiplied with the potential difference between which you're trying to move them. So VAB. So VA minus, so I write it as Q naught into VA minus VB means starting to ending. If you take, what is it? Actually, I'm sorry, VBA in this scenario. Why is it so? Because you're going to take the final potential minus initial value. So V minus delta V minus. Did you understand this step? Why is it V minus delta V? Because the potential of any point on surface B, second surface is V minus delta V, on the first surface is V. So cancel both. What are you going to get? Minus Q naught into delta V. Let me call this as equation number 2. So equation number 1 says work done. Equation number 2 also says work done. Both these work dones are equal. So Q naught into E into delta L is equal to minus Q naught into delta V. Accepted? Left hand sides are equal. So Q naught into E into delta L is equal to Q naught into delta V. Accepted? So what gets cancelled? Q naught is lost. So E will be equal to minus delta V divided by delta L. And this is a very, very, very important expression. So this is a relation, guys. I lost the page. So this is a relation. E is equal to minus delta V divided by delta L. And here, let me tell you one last point. There are two important points I need to tell you. Delta V by delta L is called as potential gradient. So what is gradient? Gradient is slope. Gradient is basically slope. Okay, in physics, if you try to define something with respect to rate of change of something means what will you write in the denominator? T. So if you write T in the denominator, you use the prefix rate. If you write distance in the denominator, you use the suffix gradient. Suffix gradient for the numerator in the sense, what is in the numerator? Delta V then another. Potential. So potential is a word, Since L is in the denominator, distance in the denominator, you add the word gradient to it. For example, had it been dA divided by dx, where A is acceleration, what will you call it as? Acceleration gradient. Had it been velocity, you call it as velocity gradient, like how you would have seen it in viscosity. Right? You call it as velocity gradient. You're able to understand? So this is a very, very important point because this term potential gradient comes here and the next chapter in a device called as potentiometer also. But they both have completely different meanings. But the word is the same. So another, don't get confused, be very clear. What does this tell you? If you look at it like an expression, don't look at it like a formula. What is it telling? Electric field is equal to negative of potential gradient. That is the meaning. So if somebody asks you what is the relation between electric field and potential, you have to tell this. What will you say? Electric field is a negative of potential gradient. Is it clear? Now we understood why the name potential gradient comes. Now the second important point I need to tell you is the significance of minus sign. Anybody? No, not like that. So here the negative sign indicates that electric field is always in the direction of decreasing potential. The significance of minus sign in this context is electric field has a direction. It's a vector quantity. Electric field is in which direction? It is in the direction of decreasing potential. Means whichever direction the potential is keeping on decreasing, that will be the direction of electric field. To put it in simple terms, if I take a positive charge, right? First, second, these two are equipotential surfaces. What is the direction of electric field? This one. Correct? So tell me whether potential at 1 is greater or 2 is greater. 1 is greater. Similarly, if you go to the third one, what is going to happen? So when you go from 1 to 2, decreasing, 2 to 3, decreasing. What is decreasing? Potential is decreasing, but that is the direction of electric field. You can ask me, sir, what about negative charge? Think about it. If I take this 1, 2, 3, this 1, 2, 3, this is the direction of electric field. But which one is decreasing? 3 is greater compared to 2, compared to 1. Why? Because when you're writing the potential, you have a minus sign in it. So negative of greater values will be less. So that is the meaning. Think about it. Okay. So in both the contexts, it will satisfy. Think about it. It will take some time for you to process, but think. So did I tell you the significance? What are the 2 important points to be kept in mind? For the next derivations, I need them. So I'm going to see you only on Monday. I don't want you to forget what is the electric field is a negative of potential gradient. Don't forget it. And negative sign indicates that the electric field is in the direction of decreasing potential. These are the 2 important points. Have this in your mind. So Monday, we are going to start with a problem based on this concept. I think it is example 2.3. Example 2.3 will start on Monday. And then we'll go to the next part. See, with this, actually, I can say 50% of the chapter is over. It is a very small chapter. Because electric potential over. We found the relation between potential and electric field also. Next is capacitance. That we'll see on Monday. Maybe next week itself we can complete it. Right. Hope it is not tough, right? Right? Good. So that's it. Any other doubts?
No, sir.
Which one? Huh? For example, depends on how they ask. This is an often asked derivation. See, generally when it comes to CBSE, right, there are 3 things. One is definitions, derivations, and formulae that are needed. Okay. So derivations and theory will generally be asked for 55 marks out of 70. And 15 marks to 17 marks is generally going to be problems. For that, obviously, you need to know the formulas. All those things, anything they can ask. They can ask. See, for example, if I no, whichever is a part of your textbook NCERT, they will ask. See, for example, 5-mark questions are not asked as 5 marks. They are broken as 3, 1, 1 or 3, 2. So 3 marks will be for derivation, 2 marks will be as a problem. Here, provided you don't have case study based questions, but they are including. I'm not sure how it is going to be. Please tell me. I'm not able to understand. Oh, yesterday's problem, huh? So whenever you're writing distance, right, you need to mention that distance is with respect to which charge. Yeah, I understood. Yesterday she also got the same. You got 24 something. You got 24, huh? 24 with respect to negative charge, 40 with respect to positive charge. So you always need to mention it. Clear?
Case instead of changing all these values, why can't we consider negative point?
The direction will be different. Direction of electric field is different.
So then, if we take a discharge, means it will be attracted towards the negative point.
But the electric field direction will be in this direction. So you need to do the work to take it against. Yeah. So those who are online, any doubts, guys?
No, sir.
Not sure if they. Yeah, we can wind up now.